So today we're going to look at areas of a surface of revolution. Way back probably in middle school when you started looking at three-dimensional shapes, you found two measurements. You found the volume and you found the surface area. Well, we talked about surface of revolutions earlier this year. That's when you have a curve and rotate it around some line to create a three-dimensional solid. We learned how to find the volume of those solids. Well, today we're going to do the other measurement. We're going to learn how to find the surface area of those solids. And that's what the area of a surface of revolution is. So we'll take some curve, rotate it about a line. Think of it as if you're painting the surface of that solid, we want to know how much area that would be. So some simple shapes first. A cylinder, if you opened it up, would lay flat like a rectangle, so you could find the surface area by doing the height times what is essentially the circumference. That curved part would end up being your base there, so 2 pi r. A cone, just to show you where the surface area formula for a cone comes from. You should have seen this in geometry. Well, in trig, you saw that theta equals s over r, where theta is your angle in radians, s is your arc, and r is your radius. Well, let's say we had this cone here and we cut it and laid it flat, the surface area flat. Well, here's our angle theta, that's the same. Our radius is the same as the slant height was, the L. So L went in this spot. And then our circumference becomes this arc. Well, our circumference formula is 2 pi r, so that's why the 2 pi r went here, because that was our arc. Now they say here that our area of a sector is 1/2 L squared pi, where L is your arc length. Let me show you where that comes from. Back in geometry, when you wanted to find areas of a sector, you use proportions, like theta over 360 equals your area of the sector over pi r squared. Well, let's just sub in the things we're working with here. We've still got theta. We're using radians, so instead of 360, we're doing 2 pi. We're going to find the area of our sector, and our radius, we said, was L. Well, if you multiply both sides by pi L squared, you get pi L squared theta over 2 pi equals your area of the sector. The pi's cancel out, and dividing by 2, that's your 1/2, and you've got L squared theta. So that's where the area of the sector part comes from. So we said the area of the sector should be this. Well, we also had that theta was equal to 2 pi r divided by L. 1/2 times 2, those wipe out to 1. One of the L's cancels out, and you get pi times the radius times the slant height, which was the exact same formula that you used in geometry. Well, but we know it's not always going to be that easy. What about more complicated things? In general, we're going to follow the same strategy we've used in other topics. We're going to slice it up into small parts, make those small parts even skinnier, and add them all up, so it'll eventually be an integral. When we slice this, the region that we're going to have will look something like this. Basically what that is, we'll have a bunch of those. It's almost like you have a cone and you chop the top off. And then we'll have to find the surface area of that region that's left. So essentially we have this. And that can be referred to as a band or a frustum. So this band, again, is like we had a cone and cut the top of the cone off, and each of our slices are going to have that surface area. So again, here's like a weird curve. We rotate it around the x-axis. We could slice it into parts, and notice we get a band, just like we saw a second ago. Think of it like a cone. We chop the top of the cone off. So we are going to derive our surface area formula. To do that, we've got some things labeled in our picture. R2 will be the radius of the cone. R1 will be the radius of the top of that band section. L1 will be the slant from the tip to the start of our section, and L will be the slant of our actual section we want. Well, we know pi times r times the slant height is your surface area. So first we're going to do the surface area of the hole minus the surface area that's not needed. And when you do that, that leaves us with the surface area of what we want. Well, again, pi r times a slant is your surface area. So we'll have pi. In our whole thing, our radius is r2. And our slant for the whole thing would be that L1 plus L. Minus the part we don't want, we'll have pi times R1, and that part's slant is just L1. So now we're going to do some algebra to do some rearranging. We'll distribute the pi R2. So we'll have pi R2 L1 plus pi R2 L minus pi R1 L1. Everything has a pi, so we can pull it out. And when I rewrite this, I'm going to write the L1s next to each other. So we'll have R2 L1 minus R1 L1 plus pi R2. Sorry, not pi R2. R2L. We took the pi out. Well, in here, we can pull a L1 out. So we'll have pi L1 times R2 minus R1 plus R2L. Well, using our picture, we can set up similar triangles. L1 corresponds to L1 plus L, and R1 corresponds to R2. When we cross multiply, we get R2L1, and when we distribute the R1, we get R1L1 plus R1L. We're going to get the L1s on one side together, so we'll subtract the R1 L1 over, and that'll give us R2 L1 minus R1 L1 equals R1 L. Pull out the L1, and we've got R2 minus R1 equals R1 L. Well, notice our left side is exactly what we have here. So we're just going to do a replacement. We'll replace that with what we know it's equal to. We'll replace that with R1L. So we've now got pi times R1L plus R2L. We can pull an L out of each of those, so that's pi times L times R1 plus R2. You may remember from when we did shells, we defined plain old R to be the average of R1 and R2. Well, we're going to do the same here. In order to get that average, R1 plus R2 over 2, we've got to divide by 2, but to keep it balanced, we'll have to put a 2 out front. Well, now we have an R1 plus R2 over 2, so this just becomes 2 pi L times R, or as we're more used to seeing it, 2 pi R L. L is our arc length. We already have a formula for that. It's square root of 1 plus the derivative squared. We'll have our radius. Often our radius will be f of x if we're going around the x-axis, but in general it's just whatever we get for our radius. And then we've got our integral from a to b, and we've got our dx. So that is our formula for our surface area of our surface of revolution. There's it written out nice. Now again, just keep in mind that f of x is really just whatever the r is. There might be cases where it's not really f of x, it might just be an x or something. Now just like an arc length can be done in terms of x or y, the surface of area of revolution can also be done in terms of x or y, depending which one might be easier. So let's look at an example. We're going to take y equals the square root of 4 minus x squared, which is really just a circle, the top half of a circle, I should say, and we're going to take it from -1 to 1. So really what we're doing is we're taking this curve here, we're rotating it around the x-axis, and we're going to find the surface area. Well, our area of surface of revolution has our derivative squared and the plus 1. So let's do that first, because we will end up needing it. Think of that as being raised to the 1/2, so our derivative will be 1/2 4 minus x squared times the derivative of the inside, which is -2x. When we neaten that up, -2x times 1/2 will be -x times 4 minus x squared. And this should also be to the -1/2 now. So that's really -x over square root of 4 minus x squared. And now we'll square it. Well, that'll give us x squared over 4 minus x squared. And we're just going to add 1 now. Now, when we add 1, I'm going to add it in a fancy way. I'm going to add 4 minus x squared over 4 minus x squared. That way, we'll already have a common denominator. And that's a technique you can sometimes do to be clever. And you'll see it'll end up working out nice eventually. So our denominator is 4 minus x squared. In the numerator, the x squareds add to 0, so we just have 4. This is all going to go under the square root now. So we'll have square root of 4 over 4 minus x squared. We'll have a dx on the end. Our x's, we were going from -1 to 1. We have our 2 pi in our formula that I'm just going to stick out front. And now we need our radius. Well, our radius goes from our curve to where we're rotating around. Well, that's just a vertical line connected to the x-axis, so that's just y. But we can't put in y because we have dx. We have to put in what y is equal to, which is square root of 4 minus x squared. Well, if we neaten up that second radical, that's really 2 over the square root of 4 minus x squared. Notice we have a 4 minus x squared both top and bottom. Those cancel out. So this is really just the 2 times 2 pi, or 4 pi dx. And this should be a really, really simple antiderivative to take because 4 pi is a constant. So all we'll do is we'll tack on an x. We'll have 4 pi x evaluated from -1 to 1. So we'll have 4 pi times 1 minus 4 pi times -1. Well, that'll just be 4 pi, and now a plus 4 pi to give us 8 pi altogether. And that is the area of our surface of revolution. So next example, we're going to take y equals x squared from 1, 1 to 2, 4, and we're going to rotate it about the y-axis. So we're going to take this right here. And with this one, we're going to show you that you could do it either with x's or with y's. Let's first do it with x's. So we'll start with y equals x squared Derivative will be 2x. Derivative squared will be 4x squared. And when we add 1 to it, we'll just have 4x squared plus 1. So our integral is going from 1 to 2. We'll have the 2 pi out front. Under our square root is the 4x squared plus 1. We'll have our dx, and then we'll have to figure out our radius. Well, this distance is our radius. It's connected to the y-axis, so it's just an x. Well, to take this antiderivative, we're used to having an x under our square root, but we've got 4x squared plus 1, so this will be a u case. Your du will end up equaling 8x dx. Well, this is where it's helpful we have that x there. We really have x dx, so we'll multiply both sides by 1/8, and we'll be good to go. I'm going to put the 1/8 out with the 2 pi. 1/8 times 2 pi will give us pi over 4. We'll have u to the 1/2, because that was square root of u, and then we'll have our du. Well, we'll end up with u to the 3/2 with a 2/3 out front. We need to evaluate from 1 to 2, and we've got the pi over 4 out front. You can go ahead and pull the 2/3 out. 2/3 times pi over 4 will give you 2 pi over 12, which is the same as saying pi over 6. And I'm going to go ahead and sub in what u was, which was 4x squared plus 1 to the 3/2, and we still have to evaluate from 1 to 2. So we will have pi over 6 times, when you sub in the 2, 2 squared is 4, 4 times 4 is 16, plus 1 is 17, so you'll have 17 to the 3/2, minus, when you sub in 1, 1 squared is 1, times 4 is 4, plus 1 is 5, so minus 5 to the 3/2. I would suggest leave it just like this. So now we're going to do the same problem and do it in terms of y. So remember we had y equals x squared with points 1, 1 and 2, 4. So if we want to do it in terms of y, we need to know what x equals. X will equal square root of y. So when we take our derivative, that'll be 1/2 y to the negative 1/2. That's like saying 1 over 2 square root of y. When we square that, we'll get 1 over 4y. And then we'll add 1 to that. So under our square root will be 1 plus 1 over 4y. We'll have a dy. Our y values go from 1 to 4. We'll have our 2 pi out front, and we need to find our radius. Well, our radius was attached to the y-axis, so that's x. But we can't put x in because we're in terms of y, so our x is really square root of y. So what we'll do is we're going to distribute that square root of y, since they're both under a square root. Y times 1 is y. Y times 1 over 4y will give us 1/4. Oops, no equals, just dy. We're used to having just a plain old y under the radical, so this is going to be a u case. U will be equal to y plus 1/4. Du will be equal to just 1 dy. So we won't need to make any adjustments. We'll just have 2 pi from 1 to 4 of u to the 1/2 dy, or du, sorry. So we will have u to the 3 halves, 2/3 out front, from 1 to 4 of 2 pi. We'll pull that 2/3 out front to give us 4 pi over 3. We'll sub back in the u, which we had was y plus 1/4. So this is y plus 1/4 to the 3 halves, going from 1 to 4. And when we sub in, we'll get 4 pi over 3 times 4 plus 1/4. Well, if you want to do it with fractions, 4 is really 16/4, so that'll give us 17 over 4 to the 3 halves. When you plug in 1 is really 4/4. 4/4 plus 1/4 is 5/4, so we'll have 5 over 4 to the 3 halves. Now you might say this does not match our other answer. It is equivalent, and we'll show you why. That 4 to the 3 halves that is in the denominator, that means take the square root of 4 and then raise it to the third. Well, square root of 4 is 2, raise the third is 8. So we're really going to have an 8 that comes out in the denominator. 3 times 8 is 24, and 4 over 24 is 1/6. So that will give us the pi over 6, and then we'll just be left with the 17 to the 3 halves minus 5 to the 3 halves, which then ends up being exactly the same as what we got before. Now, we just did this last step so you could see that it's equivalent. If you did this in terms of y's, I would suggest just leave your answer right like this. That's all for today's video. We'll see you next class, period.